Now we're going to go over the full hypothesis test from top to bottom for a single proportion. So this first page lays out all of the steps and what goes into each piece. So our parameter is P because we're going to be talking about a population proportion. So step one is set up your hypotheses statements. So if it's two-tailed, left-tailed, right-tailed, we always start with P, our parameter. The null is always equal. The alternative shows the sign for what we're trying to determine. And then we have our null value, so what we know to be true before our study begins. Step two, check your conditions or your requirements or assumptions, all the same word. Step three, calculate your test statistic. This P sub 0 is basically just reiterating that this comes from the null statement. So remember, we assume the null is true until we make our decision. So we're assuming P is the truth until we get to step 5. Step 4 we will do using both methods, the p-value and the critical value. We'll make a decision using both methods, and then we'll state our conclusion in terms of the problem. So let's do example 10. We have 2 major college entrance exams that a majority of colleges accept for admission, the SAT and ACT. ACT looked at historical records and established 22 as the minimum score on the ACT math portion of the exam for a student to be considered prepared for college math. Then in parentheses, it gives you a note that says being prepared is defined as that there's a 75% probability of successfully completing college algebra in college. This is a note. This is not important to us, so I'm going to go ahead and mark that out. An official with the Illinois State Department of Education wonders whether less than half the students in her state are prepared for college algebra. She obtains a simple random sample of 500 records of students who have taken the ACT and finds that 219 are prepared for college math. So they scored at least a 22 on the math portion of the ACT. Does this represent significant evidence that less than half the students in the state of Illinois are prepared for college mathematics upon graduation from high school? Use alpha equals 0.05 as our level of significance. That's a lot of information. It's very, very wordy. So what we're going to do first is we're going to go back through the problem and figure out what's important to us. So the first question I have is this means or proportions? And we're talking about proportions. So it tells us we're looking at well, I was looking for the word percentage or proportion. It doesn't actually say that. But it also doesn't say anything about the mean or the average. And we're talking about a number of people out of a total. So a proportion. So now we can go through and pull all the numbers that we think are important. Is 22 important? 22 is part of this definition. They've defined that as a cutoff value that separates our two groups. So you either scored above a 22 or above, or you did not. So those are your two categories. If you scored a 22 or above, you would be considered a success. If you didn't, you would be considered a failure in this binomial sense that we're referring to. But this has no bearing on our calculations. So we keep going. We have this 500. This is the sample size. This is the number of people that we've sampled. It also tells us we have a simple random sample. We'll need that shortly. Out of these 500, we have 219 that are prepared for college math. So we call this X, and we're going to use it to calculate p hat. So remember, p hat is X over N. We can calculate it now, we can calculate it later, it doesn't really matter. I'm going to wait because we don't actually need this value just yet. We were given alpha. You'll always be given alpha. If you're not, assume alpha is 0.05. Common alpha values are 0.01, 0.05, and 0.10. Okay, so we're ready to set up our hypothesis statements. So we have a null, we have an alternative. We know we're talking about proportions, so we've got P. And so we need to figure out our status quo value. So typically we'd expect to find P equals something over here, but we don't have that. So what is P? If you're not sure, go back to the question and see what you're trying to figure out and figure out what your alternative hypothesis statement would be. So the question says, does this represent significant evidence that less than half? So less than, and we can write half as a decimal or a percentage. So this is going to be our status quo value. So then the null statement, we write P equals to 0.5. And as we did previously, we're going to state the tailedness. So since our inequality points to the left, this is a left-tailed test. Step 2 is to check your conditions, your requirements, your assumptions. So step 1, hypothesis statements. Step 2, requirements. So we were told we have a simple random sample. So our sampling method is good. And we need to check n times p and n times q. Well, n is 500. And P comes from our null statement, which is 0.5. Half of 500 is 250. That's definitely greater than 5. And then N times Q. So again, N is 500 and Q is 1 minus P. So 1 minus 0.5 still leaves us with 0.5. And this one's good as well. So our conditions have been met. We feel very comfortable moving on. Step 3 is to calculate your test statistic. So our test statistic for proportions is p hat minus p over the square root of p 1 minus p over n. Well, p is 0.5 and n is 500, but here's where we need our p hat. So we can do this quick calculation here, and p hat is 0.438. So plug everything into your test statistic. And calculate. If you're plugging this all in to your calculator at one time, make sure you put parentheses around your numerator. And then when you divide, everything goes under the square root. If you break this up into pieces to do your calculation, then take all of these values out to 5 or 6 decimals until the very end. And so what you should get is negative 2.77. This is our test statistic. So step 4 we're going to do twice. The first way is going to be finding the p-value, and then we'll go through 5 and 6, and then at the very bottom we'll come back to steps 4 and 5 using the critical value method. But the p-value is the probability of being more extreme than our test statistic. We have a left-tailed test, so we're going to be looking for area to the left, and our test statistic is a z-score. So steps 3 and 4 you've done before. Back when we did sampling distributions and probabilities, you had to find your z-score and then look the area up in the table. All we're doing is calling this a p-value. So when you look up negative 2.77 in your z-table, so remember negative 2.7 down the left side, and then the column that has 7 across the top, and 0.0028 is our p-value. If this was a right-tailed test, we would need to then subtract this from 1. to get the area to the right. A two-tailed test we will actually practice next, so I'll explain that then. Now we need to make a decision. Well, our p-value is 0.0028, alpha is 0.05, and we reject the null if our p-value is less than or equal to alpha. So is our p-value less than or equal to alpha? The answer is yes. So our decision is to reject H naught. Remember, when we reject the null, we are claiming the alternative is the new truth. So when we write our concluding sentence, we say there is sufficient evidence to conclude that less than half of the students in the state of Illinois are prepared for college mathematics. So when we reject the null, we say there is sufficient evidence. And then tell me what the alternative says. There's sufficient evidence to conclude, and all of this is H1. So where did all this come from? Well, H1 says P is less than 0.5. So you can either rewrite the proportion, so there's sufficient evidence that the population proportion is less than 0.5, but I want you to tell me what that represents. So what I typically do is I reword the question into the concluding sentence. For instance, the proper way to answer the question, if I ask you, what is your name? The proper response is, my name is. So you reword the question and answer it. So the question says, does this represent significant evidence that less than half the students in the state of Illinois are prepared for college mathematics? And you could have even taken it farther if you wanted. So my answer is, there is sufficient evidence to conclude, and then everything I just bracketed off. All right, now we're going to do step 4 and 5 again, but this time using the critical value. When we look up a critical value, we need to know two things. We need to know the tailedness of the test, and we need to know alpha. And if you look in your Z table, so for confidence intervals, we looked over here for critical values. Now we're going to look over here to the right. And so you're going to match alpha is 0.05 with a left-tailed test. So we call this Z star, and it is negative 1.645. So draw your Z distribution, which is centered at 0. We're going to plot the critical value first and shade to the outside. Then you take your test statistic and plot it. So our test statistic was negative 2.77. It's going to fall to the left of negative 1.645. Since our test statistic is in the shaded region, our decision is to reject the null. So first, notice we rejected using both methods. That should be the case every single time. Second, what I notice most here is that students confuse which one to mark first. So I've got two quirky ways to remember. One, if you are in the medical field, for instance, a hospital, and two patients come in and one of them is in critical condition, you treat them first. So treat the critical value first, or mark the critical value first. Then mark your test statistic. The other way of thinking about it is our critical value we call Z star. And so stars or celebrities get preferential treatment, so they go first. So the critical value, the Z star, gets plotted first. You always shade to the outside, then plot your test statistic. Let's do another problem. The drug Prevnar is a vaccine meant to prevent meningitis. It is typically administered to infants. In clinical trials, the vaccine was administered to 710 randomly sampled infants between 12 and 15 months of age. Of the 710 infants, 121 experienced a loss of appetite. Is there significant evidence to conclude that the proportion of infants who receive Prevnar and experience a loss of appetite is different from 0.135, the proportion of children who experience loss of appetite with competing medications? Use alpha equals 0.01 as your level of significance. So the first question, proportions or means. We're talking about proportions. So let's figure out everything that we have. We have 710. 12 and 15 are not part of our calculations, so we don't need to worry about that. Then we have 121. So similar to the last problem, it says out of this 710, we have 121. So that's our x. Again, we'll use it to get p hat. And then we have this 0.135, and it tells us this is the proportion of children who experience a loss of appetite with competing medications. This is our p. This is our status quo value. So let's set up our hypothesis statements. Again, we're talking about proportions, so we have p. Our status quo value is 0.135. And so for the null, we're just going to rewrite this. P equals 0.135. But this time, we're trying to see if the proportion is different. So different means not equal to. We don't know if it's less than. We don't know if it's greater than. So this is a two-tailed test. Now we can check our conditions. And we know that we have a random sample. So we have a representative population. And then we need to check NP and NQ. So N is 710. P is 0.135. Q is 1 minus 0.135. And both of these check out. So all of our conditions are met. We feel comfortable moving on. If the conditions weren't met, then we would need to make a note that says proceed with caution before we move forward. So now let's calculate the test statistic. In order to do this, again, we need p hat, which is 121 over 710, and this comes out to 0.17. So here's our test statistic formula. Again, if you plug this all in at once, make sure you put parentheses around your numerator. And what we end up here with is 2.73. This is our test statistic. So now we need to find a p-value. So if you go to your flow chart, it says we have a two-tailed test. The question is your test statistic positive or negative? Ours is positive. So there's two ways you can do this. Our ultimate goal is the probability z is greater than 2.73, and then we're going to multiply that by 2. So you can look up 2.73 and subtract from 1, because that will give you area to the right, and then multiply by 2. So 2 times 1 minus, The probability z is less than. So this means find the area to the left directly in the table. Subtracting it from 1 gives you area to the right, and then we multiply by 2. Or I can save you one step. This is a symmetric distribution, the z distribution, right? The standard normal. It's centered at 0. So if we want the area beyond 2.73, that's the same as the area beyond negative 2.73. But in this case, it's negative. So we can look up the negative of this, look it up to the left, and then then multiply by 2. And when we do this, looking up negative 2.73 gives us an area of 0.0032. We multiply that by 2 to get 0.0064. This saves you from subtracting from 1. What I've seen students do is mix up the multiplication and the subtraction. They will multiply first and then subtract, and that's not right. So it's really just a preference. If you see this and think, I need the area beyond this, and you know, look it up, subtract from 1, you can go this route. And then the two-tailed at the end says, hey, multiply it by 2. If you think you'll confuse those steps, then you can, this only works for two-tailed test. Always make your test statistic negative, look it up in the table, then multiply by 2. If your test statistic is already negative, then don't worry about it. Just look it up and multiply by 2. Our decision rule is the same. The decision rule is independent of the tailedness of the test, meaning it doesn't matter if we have left-tailed, right-tailed, or two-tailed. For our decision, we are always looking to see if our p-value is less than or equal to alpha. And so is 0.0064 less than 0.01? The answer is yes. So again, we reject the null. So our concluding statement says there is sufficient evidence to conclude the proportion of infants who experience a loss of appetite when receiving Prevnar is different than 0.135. And lastly, finding the critical value, we need the tailedness of the test, and we need alpha. And when you look up alpha of 0.01, a two-tailed test, our critical values are plus or minus 2.575. Again, it's two-tailed, so we're going to have two critical values. So negative 2.575, positive 2.575. The test statistic is 2.73, which is in the shaded region, so we reject the null. You have two shaded regions, but you only have one test statistic, so it will only show up on one side. But as long as it's in the shaded region, you reject.